Hello today we are going to discuss about distillation column. Let's quickly see what we are going to discuss today. Content covered in this video. 1. Distillation principle. 2. Mode of operations which includes batch and continuous distillation. 3. Column internals which includes trays and packings. 3.1. Trays, covers sieve, bubble cap and valve trays. 3.2. Packings, packings covers random packings and structure packings. 4. How to select column internals. 5. Tray hydraulic. 6. Tray terminologies. 7. General design consideration. 8. Steps for designing distillation column. 9. Thumb rules for designing distillation column. 10. Types of distillations. So what is distillation tower? Distillation definition. Distillation is a widely used method for separating mixtures based on differences in the conditions required to change the phase of components of the mixture. To separate a mixture of liquids, the liquid can be heated to force components, which have different boiling points, into the gas phase. The gas is then condensed back into liquid form and collected. What are the uses of distillation? So distillation is used for many commercial processes, such as the production of gasoline, distilled water, xylene, alcohol, paraffin, kerosene, and many other liquids. Gas may be liquefied and separate. For example, nitrogen, oxygen, and argon are distilled from air. Distillation is by far the most important separation process in the petroleum and chemical industries. It is the separation of key components in a mixture by the difference in their relative volatility, or boiling points. It is also known as fractional distillation or fractionation. In most cases, distillation is the most economical separating method for liquid mixtures. However, it can be energy intensive. Distillation can consume more than 50% of a plant's operating energy cost. There are alternatives to distillation process such as solvent extraction, membrane separation or adsorption process. On the other hand, these processes often have higher investment costs. Therefore, distillation remains the main choice in the industry, especially in large-scale applications. Now let's talk about mode of operation. Distillation towers can be classified into two main categories, based on their mode of operation. The two classes are batch distillation and continuous distillation. In batch distillation, the feed to the column is introduced batch-wise. The column is first charged with a batch and then the distillation process is carried out. When the desired task is achieved, the next batch of feed is introduced. Batch distillation is usually preferred in the pharmaceutical industries and for the production of seasonal products. On the other hand, continuous distillation handles a continuous feed stream. No interruption occurs during the operation of a continuous distillation column unless there is a problem with the column or surrounding unit operations. Continuous columns are capable of handling high throughputs. Besides, additional variations can be utilized in a continuous distillation column, such as multiple feed points and multiple product drawing points. Therefore, continuous columns are the more common of the two modes, especially in the petroleum and chemical industries. Next important part is column internals. Column internals are installed in distillation columns to provide better mass and heat transfers between the liquid and vapor phases in the column. These include trays, packings, distributors and redistributors, baffles and etc. They promote an intimate contact between both phases. The type of internals selected would determine the height and diameter of a column for a specified duty because different designs have various capacities and efficiencies. The two main types of column internals discussed in this guideline are trays and packing. There are many types of trays or plates, such as sieve, bubble cap and valve trays. Packing, on the other hand, can be categorized into random and structured packing. In random packing, rings and saddles are dumped into the column randomly while structured packing is stacked in a regular pattern in the column. If we talk about sieve trays then. Sieve deck tray is perforated plate with holes punched into the plate, usually has holes 3/16 inches to 1 inches diameter. Vapor comes out from the holes to give multi-orifice effect. The vapor velocity keeps the liquid from flowing down through the holes. Weeping. The number and hole size are based on vapor flow up the tower. The liquid flow is transported down the tower by downcomers, a down and overflow device on the side on the plate. Sieve deck tray has a minimum capacity approximately 70%. Advantages. Simple construction, low entrainment. Low cost, low maintenance cost. Low fouling tendency. Disadvantages. Less flexible to varying loads than other two types. Next is bubble cap tray. A bubble cap tray is perforated flat which has a riser, chimney, for each hole cover with a cap mounted. Usually equipped with slots to allow the passage of vapor, then the vapor will contact with liquid forming bubble on the next tray. It is able to operate at low vapor and liquid rates, less than 2 GPM per foot of average of flow width. Advantages. Moderate capacity. Most flexible, high and low VAP. And liquid rates. Can provide excellent turndown. Disadvantages. High entrainment. High fouling tendency. High cost. High pressure drop. Valve tray. Valve tray is using valve which is rises vapor rate increase and then reduces vapor rate fails. This stop the liquid from weeping. Valve can be round or rectangular, with or without caging structured. Valve disc rises vapor rate increase. Valve tray has minimum capacity approximately 60%. Advantages. Excellent liquid/vapor contacting. Higher capacity. Higher flexibility than sieve trays. Can handle higher loadings. Low pressure drop than bubble cap. Disadvantages. High installation cost. Packing. Random packings. Structure packings. The selection of column internals. The selection of column internals has a big impact on the column performance and the maintenance cost of a distillation tower. There are several choices of column internals and the two major categories are trays and packing. The choice of which to utilize depends on their 1. Pressure. 2. Fouling potential. 3. Liquid to vapor density ratio. 4. Liquid loading, and 5. Most importantly, the life cycle cost. Figure shows a schematic diagram of an example distillation column or fractionator. The feed enters the column as liquid, vapor or a mixture of vapor-liquid. The vapor phase that travels up the column is in contact with the liquid phase that travels down. Column distillation is divided 2 stages. There are rectifying stages and striping stages. A. Rectifying stages. The process above the feed tray is known as rectification, where the vapor phase is continually enriched in the light components which will finally make up the overhead product. A liquid recycle condenses the less volatile components from rising vapor. To generate the liquid recycle, cooling is applied to condense a portion of the overhead vapor, its name reflux. B. Stripping stages. The process below the feed tray is known as stripping, as the heavier components are being stripped off and concentrated in the liquid phase to form the bottom product. At the top of the column, vapor enters the condenser where heat is removed. Some liquid is returned to the column as reflux to limit the loss of heavy components overhead. At each separation stage, tray or stage in the packing, the vapor enters from the stage below at a higher temperature while the liquid stream enters from the stage above at a lower temperature. Tray hydraulic. Tray design is combination theory and practice. Tray dimensions are kept within the range of values known to give satisfactory performance. 1. Provide good vapor-liquid contact. 2. Provide sufficient liquid hold-up for good mass transfer, high efficiency. 3. Have sufficient area and spacing to keep the entrainment and pressure drop within acceptable limits. 4. Have sufficient downcomer area for the liquid to flow freely from tray to tray. Tray terminologies. 1. Tray spacing. Tray spacing is the distance between two trays. Generally tray spacing ranges from 8 to 36 inches. Prime factor in setting tray spacing is the economic trade-off between column height and column diameter. Most columns have 600 mm tray spacing. Cryogenic columns have tray spacing of 200 to 300 mm. See this table for reference. 2. Outlet weirs. An outlet weir maintains the desired liquid level on the tray. As the liquid leaves the contacting area of the tray, it flows over the tray weir to enter into the downcomer. 3. Downcomer clearance, HCl. This is the vertical distance between the tray floor and the bottom edge of the downcomer apron. The normal practice is to use a downcomer clearance of ½ inch less than the overflow weir height to provide a static liquid seal. 4. Downcomers. Passage of liquid from the top tray to the bottom of tray occurs via downcomers. Downcomers are conduits having circular, segmental, or rectangular cross-sections that convey liquid from upper tray to a lower tray in a distillation column. 5. Turndown ratio. Turndown ratio defines the range of vapor load between which the column can operate without substantially affecting its primary separation objective, that is fractionation efficiency, or over which acceptable tray performance is achieved. The tray efficiency stays at or above the design value throughout the turndown range. Now most important part is designing of distillation column. So start with general design consideration. 1. Process design. 2. Mechanical design. The purpose of the process design is to calculate the number of required theoretical stages, column diameter and tower height. On the other hand, the mechanical design focuses on the tower internals and heat exchanger arrangements. Many factors have to be considered in designing a distillation column, such as the safety and environmental requirements, column performance, economics of the design and other parameters, which may constrain the work. The first step in distillation column design is to determine the separation sequences, which depends on the relative volatility and concentration of each component in the feed. King has outlined a few design rules as follows. 1. Direct sequences that remove the components one by one in the distillate are generally favored. 2. Sequences that result in a more equal molar division of the feed between distillate and bottoms products should be favored. 3. Separations where the relative volatility of two adjacent components is close to unity should be performed in the absence of other components, reserve such a separation until the last column in the sequence. 4. Separations involving high specified recovery fractions should be reserved until last in the sequence. Now the steps for designing distillation column. 1. Performing a material balance for the column. 2. Determining the tower operating pressure, and/or temperature. 3. Calculating the minimum number of theoretical stages using the Fenske equation. 4. Calculating the minimum reflux rate using the Underwood equations. 5. Determining the operating reflux rate and number of theoretical stages. 6. Selection of column internals, tray or packings. 7. Calculating the tower diameter and height. These are the thumb rules for designing distillation column. So every time before designing we can use the experience and make the use of this thumb rules. Some general design rules that should be considered are as follows. 1. Distillation is usually the most economical method of separating liquids. 2. For ideal mixtures, low pressure, medium temperature, and non-polar, relative volatility is the ratio of vapor pressures, that is alpha equals P2/P1. 3. Tower operating pressure is determined most often by the temperature of the available cooling medium in the condenser or by the maximum allowable reboiler temperature. 4. Tower sequencing. A. Easiest separation first, least trace and reflux. B. When neither relative volatility nor feed concentrations vary widely, remove components one by one as overhead products. C. When the adjacent ordered components in the feed vary widely in relative volatility, sequence the splits in order of decreasing volatility. D. When the concentration in the feed varies widely but the relative volatilities do not, remove the components in the order of decreasing concentration in the feed. 5. Economically optimum reflux ratio is about 120% to 150% of the minimum reflux ratio. 6. The economically optimum number of stages is about 200% of the minimum value. 7. A safety factor of at least 10% above the number of stages by the best method is advisable. 8. A safety factor of at least 25% about the reflux should be utilized for the reflux pumps. 9. Reflux drums are almost always horizontally mounted and designed for a 5 minutes hold up at half of the drum's capacity. 10. For towers that are at least 3 feet, 0.9 meters, in diameter, 4 feet, 1.2 meters, should be added to the top for vapor release and 6 feet, 1.8 meters, should be added to the bottom to account for the liquid level and reboiler return. 11. Limit tower heights to 175 feet, 53 meters, due to wind load and foundation considerations. 12. The length, diameter ratio of a tower should be no more than 30 and preferably below 20. 13. A rough estimate of reboiler duty as a function of tower diameter is given by Q equals 0.5 D2 for pressure distillation, Q equals 0.3 D2 for atmospheric distillation. Q equals 0.15 D2 for vacuum distillation. Where Q, energy in million BTU per hour. D, tower diameter in feet. Types of distillations. Steam distillation. Vacuum distillation. Azeotropic distillation. Extractive distillation. Pressure swing distillation. Reactive, catalytic, distillation. First is steam distillation. Many organic compounds tend to decompose at high temperatures. Steam distillation is a special type of distillation process for temperature-sensitive materials like natural aromatic compounds. By adding water or steam in distillation apparatus, the boiling points of the compounds are depressed, allowing them to evaporate at lower temperatures. After distillation, vapors are condensed as usual, yielding a two-phase system of water and the organic compounds, allowing for simple separation. For example, the boiling point of bromobenzene is 156 degrees Celsius and the boiling point of water is 100 degrees Celsius, but a mixture of the two boils at 95 degrees Celsius. The necessary condition for employing steam distillation is that product must be practically immiscible with water. Vacuum distillation. Similar to conventional distillation except that it operates at very low, near vacuum, pressure. Allows the mixture to boil at a lower temperature and thus avoids the thermal degradation problem mentioned earlier. Separation of azeotropic mixtures. Liquid mixture that boils at a constant temperature at a certain composition. Such mixture cannot be separated using conventional distillation methods. Separation of azeotropic mixtures classified into the following methods. By addition of an entrainer/solvent. By changing system pressure. Separation by changing system pressure. Pressure swing distillation. Distillation columns are operated at different pressures, as it has been known that the azeotropic concentration can be shifted substantially by changing system pressure. As shown in the figure, the pressure change as follows. 1. Low pressure rectification, A to B. 2. High pressure rectification, C to D. 3. Low pressure stripping, E to target purity. Extractive distillation. Extractive distillation is defined as distillation in the presence of a miscible, high-boiling, relatively non-volatile component, solvent, that forms no azeotrope with the other components in the mixture. The method is used for mixtures having a low value of relative volatility, nearing unity. The solvent interacts differently with the components of the mixture, thereby causing their relative volatilities to change. This enables the mixture to be separated by normal distillation. Original component with the greatest volatility separates out as the top product. The bottom product consists of a mixture of the solvent and the other component, which can again be separated easily because the solvent doesn't form an azeotrope. Bottom product can be separated by any of the methods available. Boiling point of the solvent is generally much higher than the boiling points of the feed mixture, so that formation of new azeotropes is impossible. The high boiling point will also ensure that the solvent will not appreciably vaporize in the distillation process. Selection of suitable separation solvent. Solvent must alter the relative volatility. Quantity, cost and availability of the solvent should be considered. Solvent should be easily separable from